Hi, welcome to the Potter's Roundtable. This is Pottery Shorts, a series of short pottery topics done on the fly. Hi, this is Pottery Shorts. I'm Phil Bernberg, and today's topic is what happens to clay when it's fired. And this is actually in response to a request that we had, or a question that we received by email a while back. So here's the answer. The short answer to the question is a series of chemical and physical changes as the temperature increases with time. So there's this continuing series of changes that happen. And if you talk about clay alone, meaning just a lump of clay, not necessarily a clay body, but let's say raw clay or a local clay, if we assume that the clay is primarily consists of kaolinite, which is the major clay mineral, and this is the formula for it, aluminum oxide, 2 silicas, 2 water. I'm going to refer to that later, so I just wanted to put that up. For clay alone, the clay starts out as, this lump of clay would start out as consisting of clay particles plus some quartz, because quartz is kind of an invariable impurity. And then there might be other chemical impurities, organic materials and other inorganic materials like iron oxide or something. And then you can talk about what happens during the firing really in terms of 5 stages that I've put on the board here. And we'll talk through these briefly. So the first stage is drying, and this is basically you're finishing the drying of the clay if you haven't already completely dried it, and so water is evaporating. If, however, you're heating the clay too quickly during the firing, and you notice I'm not specifying necessarily a bisque or a glaze firing here, just the firing. If the water changes to steam, then you have the possibility of explosions in addition to drying because of the expansion of the steam. When water turns to steam, it expands around 1,200 times in terms of volume, which is the reason why you get explosions. Basically, you create a bomb. So the first stage of the firing is basically just completing the drying. The second stage I've called decomposition or oxidation. And what that really means is this is where chemicals and things in the clay are starting to break down. So around 600 degrees Fahrenheit, carbon and organic impurities, organic materials that might be in the clay start to break down, and they start to either sort of just break down or actually burn completely and change into gases, mostly carbon dioxide and water. And then when you get a little hotter, in the range of 750 to maybe 1100 or 1112 degrees Fahrenheit, this is where the chemical water from the clay starts coming off. So referring back to the formula, for instance, for kaolinite, this is the chemical water or the structural water that's actually contained in the clay itself. So when you get up to this temperature range, 750 to 1100 to 1200, this water is actually starting to come off from the clay. And at this point, the clay loses its plasticity. It's really when that water leaves, it's no longer clay. And at the same time, you're starting to get shrinkage. Also, what happens in this same decomposition period is impurities in the clay, such as sulfides, sulfur compounds like iron sulfides or sulfates, carbonates, like for instance, if there were little limestone particles, which is calcium carbonate, they would start to break down. They decompose and they break down, and they give off gases like carbon dioxide or sulfur dioxide. And so we have a chart here, for example, that you can look at. And this chart basically shows changes that are occurring in some of the impurities with time during the heating. And without following any one of the particular curves, the point of the chart is the fact that nothing is happening almost instantaneously. It takes you have all these sort of competing or parallel changes that are happening, reactions, and they're all taking place at the same time, but they take place over a period of time. So this is one of the reasons why you don't want to do when you're firing clay, you don't want to fire it too quickly because you have to allow these changes to occur, these reactions to occur, the impurities to burn off. So that's really the point of this chart, is just to show that when you get to a certain temperature, things don't just happen and then it's done. They extend over quite a long period of time. The third sort of phase that happens during the firing, I'm calling reforming. And what that really means is I'm forming new compounds. Now that some of the previous compounds have broken down, now the chemical elements are recombining and forming in new arrangements and forming new materials. So, for example, when the water has been driven off from the clay, what was kaolin is now changed into what is called metakaolin. It's no longer strictly a clay. And then as you continue to heat it, the atoms, the aluminum and oxygen silicon atoms, move around and they rearrange themselves into new materials. And ultimately, if you heat it high enough, what they'll form is mullite, which is an aluminum silicate, and then they also give off free silica. And accompanying these changes, you have additional shrinkage in the clay. And also, under the reforming, if you had some quartz in the clay to start, the quartz would be changing to beta quartz, the higher temperature quartz. It would be going through and expanding a little bit as it goes through the transition. And if you continue to heat it up into like the cone 6 to 10 firing range, some of the quartz would actually convert to the form of silica known as cristobalite. So this is all happening as you're getting up to some of the sort of higher temperature ranges. Then finally, the fourth stage of heating, I'm calling partial melting or sintering, because when you finally get high enough, again, like cone 6 and above, roughly speaking, the particles of the material actually start bonding together. Atoms are actually moving around and sticking together, and the particles are actually joining together. That's called sintering, where they're bonding together. And in addition, if there are impurities in the clay that act as fluxes, there may be a little bit of melting occurring where the impurities act as fluxes and they melt the silica, and I might start to form a little bit of glass. And again, when I'm getting this sintering with the particles bonding together and a little bit of glass formation, I'm getting additional shrinkage of the mass of clay. And of course, at this point, if I continued to heat the clay hot enough, eventually the whole clay would just melt. And then finally, so let's say I've gotten to the end of the firing where the clay has gotten dense and I've produced some liquid, some glass in the clay. And now the firing is done, so I turn off the kiln, and now the heated clay is cooling back down. There are still some changes that occur during cooling. And one of the things, one of the main things that can happen is there can be some new materials that crystallize out of the glass. If part of the clay has melted earlier in the firing to form a glass, during cooling, new materials can crystallize out of that. One of them is mullite again. The formula for mullite is this. It's an aluminum silicate compound. It's 3 molecules of aluminum oxide and 2 of silica. So you can see, in a sense, how you could produce mullite from kaolinite. You combine the aluminum oxide and silicon oxide in different proportions, and you lose the water, basically. And mullite is one of the materials that in a fired clay body adds considerably to the strength and the shock resistance of the clay body. So this is actually a good thing. It's a desirable thing. It's not something we want to avoid. And the other thing that can happen out of the glass is you could also crystallize out some cristobalite. So those are the main changes that would happen to the clay when it's fired. If you had a clay body, now you have the additional reactions that are occurring because of all the flux that you haven't now intentionally added to the clay body. So if you've added, let's say, feldspar, a soda feldspar, or a potash feldspar, or you've added methylene cyanide, as you get up to around 2,000 degrees Fahrenheit, these are going to actually react with the silica in the clay body and form additional melt. So you're going to form a lot more glass because you have added these fluxes, which means that you're going to get accelerated shrinkage and accelerated sintering and bonding of the particles brought about by the glass. And again, even with the presence of flux, if you have quartz in the clay body, some of that quartz is going to convert to cristobalite. So that sort of describes the sequence of changes. Some of the important points to think about is that a lot of these changes overlap. You can't give specific temperatures and say, well, at this specific temperature something happens. I think that chart was a good example of how a change will start and it'll continue, and before it finishes, some other change is starting and continuing. So you have all these things going on, sort of overlapping and occurring at the same time. So again, this is the real justification for a relatively slow firing when you're firing clay. This would be like either a bisque firing or a glaze firing, because you have to allow enough time for all these things to happen for the clay to become properly mature. So at the end of the firing, basically, the clay ends up cleaner than it started out because some of the impurities, like the organic materials and some of the sulfides and sulfur compounds, have been burned out of the clay. The clay is denser and stronger than when it started, and a lot of the holes, the pores, and tiny little pores have been eliminated. The clay is certainly stronger and harder than when it started. And now it consists of two new materials. Instead of being clay and fluxes, in general, the fired clay is going to consist of mullite, plus some crystalline silica, maybe quartz and or cristobalite, and some glass. And so the clay has changed basically into a new combination of materials as a result of the firing. Well, I hope this has been useful, and I hope it answered the question of the person that was interested in talking about what happens during a firing. Thanks for joining us. Thanks for joining us today. If you enjoyed the presentation, please like it and subscribe to our channel and share it with your friends. This way we get more viewers of our videos. Also, check out our website, www.hfclay.com. We'd really like to thank our patrons for supporting our educational efforts, such as these videos. And if you'd like to consider becoming a patron, go to patreon.com and look for the Potter's Roundtable.